right, welcome. We're going to be looking at something called the extreme value theorem here. And so here we have this scenario about stock values, stock prices. So it says stock prices vary from day to day, making investments risky. How can we analyze the value of a stock over time, and how could this help us make predictions for what will happen in the future? So again, we're going to be looking at what are called extreme values. Extreme meaning the highest and lowest values of a function. Okay. The value of Apple stock over a 14-day period can be modeled by A of t, where t represents the days after May 31st, and A of t is measured in dollars. The graph of A of t is shown below. Okay, so here we can see our graph. The y-axis here, this is our dollars for the stock value. And then these are our days along the x-axis. Again, we can't really see the x-axis here, but this would represent day 0, day 1, day 2, 3, 4, and I'll keep labeling these just so that it'll be easier to kind of talk about. And then finally, day 14. So we're looking for a 14-day period. Again, this is after May 31st, so this would be May 31st. This would be one day after that, June 1st, and so on. All right, describe what is happening to the value of the stock over the 14-day period. All right, so I went ahead and typed this out because it's kind of a long thing here, but let's see if we can kind of interpret what's going on. So it says the stock value begins around $226. Okay, so you can see, that seems reasonable. And it decreases over the first day. So as we kind of follow this, right, it's decreasing, decreasing, decreasing over that first day. And this would be kind of the end of the first day, right? Day 0 is where our interval starts. Then day 1 is kind of the end of the first day, the end of the second day, end of the third day, end of the fourth, end of the fifth, end of the sixth, and so on. I'll just kind of make these points here so we can talk about it a little more clearly. And yeah, finally, okay. Next, the stock value increases. So after the first it decreases, it increases all the way to around $227. I guess that wouldn't be correct. That wouldn't be $227. I think that would be 217. Yeah, like right around here would be about 217, just a little bit over 216. And that happens somewhere between day 3 and 4. And yeah, that's where we're seeing that. Then the stock value decreases. Okay, it's decreasing, decreasing all the way until day 12. Yeah, somewhere between day 12 and 13 here, right? It's happening to a value of around 185. Yeah, so that's below 186, seems reasonable. And then finally, the stock value increases sharply over day 13, maybe even day 14. I'm not really sure there, right? This would be the end of day 13 and the end of day 14. Yeah, so maybe like during day 14 to a value of around 209. And yeah, that seems reasonable. Again, there's a lot of different things we could label and talk about on this graph. I just decided to talk about how it was increasing and decreasing and what maybe some of these maximum and minimum values were. All right. What is the highest value of the stock during this time period? What is the lowest value? Okay, so our highest is all the way up here at the very beginning. So our highest is, we called that $226. So 226, and then we had a lowest that was occurring down here, and we said that that was somewhere around $185. Again, these are approximations. I don't really know the exact answers here, but we'll kind of go with that as our approximation. Interesting that that was green. Alrighty, moving forward. Suppose you bought stock on June 1st. What was the highest value your stock reached during your first week of owning it? All right, so let's kind of take a look at that. So June 1st, that would be the first day, right? This is May 31st, so June 1st. We will kind of cut that out. So June 1st would be here, and then a week, so 7 days, 1, 2, 3, 4, 5, 6, 7. So we're only looking at kind of this interval right here. And that highest value would occur right here, at this kind of maximum, right? That's our highest because it goes up to that value and then it goes down. So if we sort of approximate that, that looks to be around $217. How does this compare to our answer in question 2? Well, obviously it's lower, right? So it was $217, which is about $10 less. We could also look at the lowest value here, and the lowest value would have occurred on this interval here at this endpoint around $201. All right, on which days is the value of the stock changing the fastest? Okay, so we're looking at the change, right? And in this case, when we're tracking the value over time, we want to know what's the highest rate of change, what's our steepest sections of this graph? When is the price changing the most? And so in that case, we can kind of look at, our steepest section. So right here in this first day, very, very steep rate of change. And then also during this last day, right, very, very steep rate of change. Now, in these other sections, that's pretty steep, happening between day 2 and 3. That is also somewhat steep. It's not quite as much as these other ones here on the endpoints, right? We have some relatively steep sections, but I would say on the first day and the last day were where we saw the greatest amount of change. So we'll go ahead and say that. Let's change that font size. On the first day, it decreased very sharply. We can see the slope of the graph is highly negative on this day. Go ahead and get that back on my screen here. On the last day, the value increased sharply. We can see that by a highly positive slope. Again, taking a look at these slopes, and again, on this first day, we saw that really sharply negative where it went from 226 all the way down to around 206. And then here on this last one was a very sharp one as well. Now, these other slopes also pretty steep, but you can see, if we just look at a single day period, the change is not quite as much as what's happening on this first day and last day. All right. For which values of t was the stock for which values of t is the value of the stock not changing? How do we know? Okay, so when is the value of the stock not changing? When is it, flat? So what we're looking for are horizontal tangent lines, right? So if we kind of sketch in a couple here, we'll go then green. We can see right up here, we would have a horizontal tangent line happening between day 3 and 4, and another horizontal tangent line happening right there. And there's actually another one in here, right in this section, where the value is not changing. It's flattens off and kind of not changing there. And again, it's flattening off, and then it's not changing in this section. And those are instantaneous rates of change, but that's happening on the 4th day, on the 8th day. And we'll just have to approximate this. We'll call this like 3.8, 8, 12.7. Okay, I'm just approximating some specific t values. So t equals 3.8, t equals 8, and t equals 12.7. Again, I'm kind of approximating, and the way we saw that is that the slope of the tangent lines were horizontal. That is indicating no change, or that it's instantaneously not changing, right? Remember, that's 0. The slope value would be 0. Alrighty, let's go ahead and take a look at some of our more formal ideas here. Okay, so we have something called the extreme value theorem. So I'm going to take a look at this. It says if a function f of x is continuous on a closed interval, then that function f of x has both a maximum and minimum value on the interval a and b. So In other words, there are two numbers, a number c and a number d, that are in our interval, such that the output for c is less than the output for our function at all values of x, and a value of d that's greater than all of our values for f of x, again, in that interval. So this one would be our minimum, and this one would be our maximum. And you can see here on this little graph here, looking from between A and B, we have a minimum value happening at C, and we have a maximum value happening at D. Now, this is not the only graph that we could have that looked like this. You know, I could sketch out something else. Let me just go ahead and just make some other random sketch here. I'll just do it over the top of this. So let's say we had a graph that was kind of like this, okay? Weird looking graph, but this is still our interval from A, right, A to B. And the highest value actually happens at the very start of our interval, right? This is the max. And then the minimum happens right down here, and this is our minimum. But they still are there, right? It still has a maximum and it still has a minimum. And this is a continuous graph, right? As I sort of trace it, it's defined everywhere. And yeah, we have a minimum and a maximum still. And again, I could draw like infinitely different graphs that kind of work here. We could even draw a linear graph, right? Line. We have a minimum at A and a maximum at D. So those the endpoints could be our minimum maximum, or they could occur kind of somewhere in the middle like we see on our original graph here. The point is the extreme value theorem guarantees that they do exist. It doesn't tell us where, it just tells us that there is a minimum and there is a maximum in that interval. Alrighty, so a couple little definitional things here. So it says f of x has an absolute minimum at x equals c if f of c is less than or equal to f of x for all x in the interval, for every value in that interval. We call it an absolute minimum, right? So if the output is lower than every other value in that interval, then that's called an absolute minimum, versus something called a relative minimum, right? F of x has a relative minimum at x equals c if f of c is less than f of x for all x near c. So if we're only looking at a certain little area around there, kind of like this, right? That's called a relative minimum. Now, this one happens to also be a absolute, but let's say this graph sort of continued down below it, right? Now it's no longer the lowest. It's just the lowest when we kind of focus in on that small section of our graph. You know, again, because we're only restricting ourselves to between A and B, we would still call this an absolute minimum on that interval. But if we extended our interval out and the graph goes below it, you know, we call it a relative minimum. All right, so same idea with maximums. You know, if we have an absolute maximum at a value d, that means that f of d is greater than f of x for all x in the interval. So this was an absolute maximum because it is the highest in the whole interval. But again, let's say we extended this out and the graph went up above it. Now, you know, this is only a relative maximum, right? Because now it is only the greatest value near D, right, near this area, but the graph does go up above it later on. Now, again, once again, we're restricting ourselves in this case between A and B, so we would consider this an absolute maximum on this interval, but if we expand our interval out, right, we could call these relative maximums. Or if we just had kind of a different graph, right? So if we just had kind of a different looking graph and it was doing some weird stuff, right? A lot of little curves and things. Any point, you know, could be, any of these points could be a relative or an absolute, right? So this one here is only a relative maximum because the graph does go up above it up here, right? But it is the highest when we look at this area. Again, this point here would be considered a relative minimum because, again, the graph does go below that value, right, at other places. So even when we restrict our interval, we could have relative maximums, relative minimums in these various places because our graph does end up going above or below those points. All right, finally, kind of our last thing here, critical points. So critical points are going to be critical to a lot of the work that we do. It says critical points are points when the derivative is 0 or undefined. That's it. So a critical point of a function is when the derivative is 0 or undefined. Our relative or absolute extrema points are going to be located at either the critical points or the endpoints of our interval. So this gives us a good way to find these relative extrema. We just need to look at the critical points and the endpoints. Yeah. So I'm going to actually kind of go down here and take a look at these two here. So I'm going to start with question number 1. So it says the graph of f prime is given below. So this is our derivative. For which x values does f of x have critical points? So we're just identifying the critical points. Again, critical points occur when the derivative is 0 or undefined. So in this situation, we have a graph of the derivative. So we're looking for places where this derivative graph is 0 or undefined. So 0 being the output of our derivative, being this place, right? Where is it equal to 0? Right here and right here. So we have x equals 1 and x equals 3. Those would be considered critical points because our derivative is equal to 0. And then we do have a point here where it's undefined. You can see here with this open circle. So at x equals 4, it is undefined. So again, I'm kind of explaining this as I go. These 2 points are when the derivative equals 0. I'll use more concise notation for that. I'll say these are values when f prime of x equals 0, and this one value is when f prime of x is undefined. Again, both of these cases would make them critical points. All right, now finally, we can also take a look at equations. Right here we had a graph, and we also can kind of look at equations as well. So it says let g of x equal 3x squared minus 8x plus 7.5, and we are going to find the critical points. So we want to know when the derivative equals 0. So we'll find the derivative of this sort of quickly. 2 times 3 will be 6, and then that becomes x to the first power. Minus 8x becomes minus 8, and then derivative of constant is 0. So we want to know when is this equal to 0. Well, that's pretty easy. This is a linear graph. We're only going to get one solution to this. We just set up an equation. We set the derivative equal to 0, and we solve it. Now, this is a technique we're going to use a lot, setting the derivative equal to 0 and solving. Depending on the equation that we get here, this could be challenging or it could be pretty easy. This one is very easy because it is a linear equation. So we'll add 8 to both sides. We'll get 6x equals 8, and then we'll divide by 6, and that will give us x is equal to, simplify that fraction, 4/3. So that is our only critical point, because this is when the derivative is equal to 0. We know that this being a linear graph, a line with a slope of 6, right, this is going to be continuous. There's going to be nowhere where it's undefined. So the only critical point we have is this one value where it happens to be equal to 0. Anyway, these are just some kind of important ideas with extreme values, finding critical points and such. We'll be using this in our next lesson. Anyway, see you then.